So, as I said, thanks a lot for having me in this event, and I feel really honored for being with you in this very special day of St. Albert the Great, who's been so inspiring for all of us in this beautiful task of getting together science and religion. So I think that we are Catholic scientists. We are also trying to develop a chapter of the Society of Catholic Scientists in Spain. So I ask your prayer for this challenge that we also have in Spain. So this is the title of my talk, An Exceptional Universe, Thoughts from Physics for Theism. I think that I'm lucky to talk about one of my favorite topics, because, well, I have the impression that in this science and religion dialogue, usually the framework is that of biology. So perhaps because in the 19th century, we had The Origin of the Species by Darwin, and so the understanding of life and of the human being changed forever. We speak about a Copernican turn. Then my impression is that maybe physics is no longer the framework to speak about science and religion. And I think that's misleading, because, of course, physics should be at the very deep level of biology and of chemistry and all those other disciplines that study emergent features of the universe. So that's one of the main reasons why I'm interested in physics in this dialogue between science and religion. But there's a second reason, I would say. And so my impression after some years working in this field of science and religion is that we are in a sort of Scylla and Charybdis situation. I will try to explain me. So usually in Christian thought, in Christian philosophy, we try to figure out this science and religion relationship through the articulation of primary cause, God himself, and secondary causes, so natural causes. Now, there is some risk in this articulation, because if we stress too much God's transcendence, then this can become meaningless for scientists, because we are speaking about such a transcendent God that, well, okay, he's the source of being, but has nothing to do with the working of the universe in itself. On the other hand, if we stress too much the divine action, and we say that, of course, God is always acting, working in the universe, we run the risk of thinking about God as the so-called God of the gaps. So as an explanation, whenever we don't understand something in nature, we don't know science enough to understand something in nature. So perhaps this is the main take-home message of my talk, that I think that we need to find a sort of via media in which we are able to combine God's transcendence and God's immanence in nature. And so in my talk, what I will try to do is to show in physics some clues that point towards the plausibility of a personal God as the creator of the universe that we inhabit. So this is the summary of my talk. You see that there are four main parts where I will speak about this singularity or exceptionality of the universe in thermodynamics, also in the question of complexity, the emergence of complexity in nature. And then I will say something about the duality that we have in our most fundamental theory of nature, of quantum mechanics. And I will be more specific in dealing with what is called in the symbol grounding problem in information. So in all this philosophy of information is one of the key terms now in science to understand the development of the universe. Perhaps if we have time, I will speak something for a while about what I consider the ultimate determination, or the ultimate singularity or complexity in nature, that is the emergence of immaterial knowledge. That's a feature reserved to human beings. Okay, so let's start with my first part. So I will speak about this thermodynamic singularity of the universe. In what sense our universe is exceptional or singular, if you wish, in the sense of not being a particular case of something more general. So that's one very basic way of understanding this word, singularity. Now, let me start with something very basic, at least from the point of view of physics. Now, imagine that we have n particles. These are the particles that compound the universe, all the particles we have in the universe. And so we could say that we have like 6n degrees of freedom, since each particle needs 3 variables for its position and 3 variables for its velocity, and we have n particles. So we could imagine an abstract space. In physics, this is called a phase space with 6n dimensions, and every point in that abstract space, phase space, represents a specific state, a detailed state of the universe. Now, think about this phase space. These pictures have been taken from Penrose's book, The Road to Reality. And now in this phase space, we have all points here are microscopically distinguishable. So there are different states of the universe. Detailed states are different. However, we have regions where these two states are macroscopically indistinguishable. So just think about a gas in a volume. So we could have the gas in a situation of equilibrium, of thermodynamic equilibrium, and we need only 2 variables, pressure and temperature, to describe macroscopically this gas. However, there are many different configurations, microscopic configurations that are distinguishable in the microstructure of this gas. However, they are macroscopically distinguishable. Now, of course, this is what is behind the definition of entropy, this quantity, this remarkable physical quantity. And maybe you're familiar with this formula. It's a Boltzmann formula for entropy. So the entropy of a state in the universe is proportional through this Boltzmann constant to log of the volume of the phase space, where all these detailed states are compatible with a single macroscopic state. Now, what is remarkable about entropy? Now, I think that all of you are familiar with the second law of thermodynamics. Now, the second law of thermodynamics says basically that the entropy of a closed system is never decreasing. So it remains constant, or it always increases. So technically, we should write down this second law as follows, as the time derivative of the entropy of the universe. Applying this law to the whole universe should be bigger or equal to 0, because it's always increasing, at least non-decreasing. Now, I'm following here Roger Penrose, and he says that what is remarkable in the universe is that so we are not dealing with a question of sheer statistics. Now, imagine that we apply this view of the phase space to the whole universe. Now, if the second law were a matter of sheer statistics, so the most likely state in the universe now would be the state of thermal equilibrium. So we should be in a state that is in the part which has most detailed states compatible with a macro state. That's the state of equilibrium of the universe. Incidentally, this would be a huge black hole. That's the most stable state of the universe. That's black holes are the objects of the universe with the biggest entropy. But this is not the situation in which we are now. So we are in a different situation. So the now is here. So we are in a part of the phase space where, well, we have some entropy, but it's a moderate amount of entropy. Now, since the fundamental laws of physics do not distinguish between past and future, So, well, of course, statistically, we could say that the second law is simply a question of following the most likely regions of the phase space. So we should evolve to the situation of equilibrium, to the most likely state, to this big state. So that's what we would expect. And of course, this is compatible with the second law. This is what the second law is saying. But if now we go backwards in time and we stick to the statistical argument, so since the fundamental laws of physics do not distinguish between past and future, we should expect that we are coming from state of bigger entropy that we are now. So from a state like this one, like this t equals 0. In t equals 0 for the universe, we should start from a region of huge entropy, because there's no difference between past and future, statistically speaking. Now, of course, C is incompatible with the second law of thermodynamics. So the second law of thermodynamics arises from what is called the past hypothesis. What is the past hypothesis? The past hypothesis says that actually the beginning of the universe is a region of a tiny, tiny entropy, of extremely tiny entropy. So something like this, it's a very singular region. Actually, we can estimate this, and this can be done, I cannot go into the details, through the Bekenstein-Hawking formula for the entropy of black holes. And basically, if we compare the singularity of the Big Bang, of the entropy in the Big Bang, and we compare it with the maximum entropy that the universe as a whole could have, you obtain this remarkable relation. So our universe is as singular as one part compared with 10 to the power of 123. So again, I cannot go into the details, but please let me stress the singularity or the enormity of this number. So this number is not a 1 followed by 123 zeros. It's a 1 followed by 10 to the power of 123 zeros. If we wish to write down that number, there is not enough space in the universe to write down that number. So again, following Robert Penrose's work, he says that this is the most profound problem of modern cosmology. Just trying to figure out why the universe starts with this extremely tiny entropy, like 1 compared with 10 to the power 10 to 123. Okay, this is a picture, an illustration of how the creator would have such hard work to find out the right initial conditions for the universe, for our universe to work. And of course, the question of entropy sometimes is misunderstood. It's a nice joke. I like to introduce, to put down this joke, because we usually tend to identify entropy with disorder, and that's why we don't teach about entropy to our children too soon in life. But so of course, entropy has to do with disorder, with the different ways a macroscopic state can be realized microscopically in detail. But the problem is not disorder. The problem is this. So we live in a universe where one of the ends of its evolution is in a region of extraordinarily minimum entropy. And extraordinary minimum is really tiny. You remember this name. Why? We don't have an answer for that. If you wish, we could discuss the question of the multiverse, but in my view, I don't think that the multiverse solves this question of entropy. And the reason is that even if we live in a multiverse, our particular universe is exceptional. And so there is no explanatory power in the multiverse picture. As Lee Smolin explains in one of his books, he says that an explanation should arrive to the typicality of our universe. So an explanation is valuable when it shows that our universe is typical in some framework. But this is precisely what we do not obtain with a multiverse picture, and of course with this problem of entropy at the Big Bang. So in a sense, the multiverse begs the question. So this, I would like to call it the first singularity. This is the thermodynamic exceptionality or singularity of our universe. So let's move on and let me talk about the complexity, increasing complexity in nature. And of course, this has to do with living systems. But let me discuss with you, well, in what sense I think that complexity is a singularity in nature. Well, maybe you're familiar with John Conway's Game of Life. So the idea of this picture, I don't want to spend time showing the video, but imagine that the universe is this set of pixels, and each pixels can be black or white, and black means that the pixel is alive, and white means that the pixel is dead. And with very basic rules, microscopic rules, I think that with 4 basic rules, for instance, depending on the number of neighbors that you have, then you can remain alive, or you can become alive, or you become dead if there is overpopulation, so if the thing is overcrowded. So with 4 basic rules, you would obtain a dynamics of this picture that is really beautiful. You would obtain patterns like gliders. Maybe you've heard about gliders in this Game of Life. And gliders interact with each other. Gliders feed themselves. Gliders engage in fight, in wars. Gliders build cities. So you have this emergence of beautiful patterns that somehow remind us of complex systems in nature. So of course, the analogy is, well, maybe life is simply based in very basic rules, and we see patterns, but these patterns are, in a sense, unreal. So they're epiphenomenal. It's not only because we don't know the details, we don't know yet the details of life, that we observe these complex configurations, but they are simply configurations. There's nothing to it. So this is the question, and in the philosophy of science, this is called weak emergence. So weak emergence tries to convey the idea that emergence, what seems to be very complex, actually is nothing else that's a specific configuration because of the initial condition and because of the macroscopic laws of nature. I also like to present this picture. It's a part of the Mandelbrot set, and so it's very beautiful in itself with this mixture of colors. And of course, this is following basic rules that a specific algorithm can reproduce. So nobody doubts that this beauty is produced by an algorithm with the colors and the rules that the algorithm must follow. Now, if you wish, this is what lies behind the idea of scientific reduction. I found this beautiful definition of reduction, of scientific reduction, by Frank Wilczek. Frank Wilczek is Nobel Prize. He worked in the theory of quarks, the asymptotic freedom of quarks, to understand how quarks combine to form protons and neutrons and so on and so forth. And so let's read at his definition of reduction. So he says that a complex object has been reduced to something simpler when it's been shown or made plausible that the more complex thing can be analyzed into simpler parts and its behavior synthesized from the behavior of those parts. So this is the idea behind weak emergence. So if we can recover what we see at the upper level from the most fundamental interactions and the most fundamental parts of the whole, then we have reduced this system into simpler parts and their interactions. So the idea, again, is that we could build reality in a bottom-up fashion. So from the bottom, from the most basic constituents and the dynamical laws, we could obtain all these patterns that, again, are no more than specific configurations of things, of fundamental things, the fundamental parts of physics that we don't know yet what they are. Now, let me put this scientific reduction and this weak emergence into a big question mark. So the point is, can it be done with everything? So does nature really work like that in this bottom-up fashion? So let me show you, this is a beautiful picture. It's a milk drop hitting the ground, and then the rebound gives us this beautiful crown with 24 peaks. Now, if you know something about symmetry, you could say, well, of course, the spherical symmetry is broken, and now we obtain a less perfect symmetry with these 24 peaks, but at least there is still some symmetry in the picture. So my question is, can we recover this idea of symmetry breaking and these 24 peaks just with initial conditions, with a very basic dynamical laws, or there is something deeper going on here? So complexity has to do with this emergence of patterns and patterns of patterns. So perhaps the basic example of complexity in physics is this phenomenon of Pyramidal cells. If you have a liquid and this liquid is heated and there is some gradient of temperature between the top and the bottom, when you reach some limit, so there's this development of pyramidal cells. So there appears these hexagonal structures, and it's marking the change, the transition from a conduction regime in the heat transfer to a convection regime. So now the moving of the liquid is important to dissipate the heat. So we have the appearance of these hexagonal pyramidal structures, that it's really beautiful. Now the question is, why these hexagonal structures? Can we predict that from a bottom-up fashion? So complexity, at least from the point of view of a physicist, I think has to do with these three features. First of all, we have different levels of description. Let me tell you why. Well, because of course, in the case of the milk drop, these 24 peaks are relevant because I'm able to count peaks. But in the atomic level, so atoms don't care too much about whether they form peaks or not, or whether they are dispersed enough. Or think about the Pyramidal cells. For the atoms and molecules, so these hexagonal structures are not relevant in the macroscopic description. So they are relevant as patterns for us when we are able to individuate them, so as specific structures, specific patterns that are somehow not disordered, so they keep some form. So these things happens. Complexity appears in nature when we have different levels of description, relevant levels of description. When we have far from equilibrium systems, so usually we live in we have a dissipative regime. So this has to do with Prigogine work on non-equilibrium thermodynamics. So of course the paradigmatic case of complexity in nature are living systems. So living systems keep a low entropy, dissipating continually energy. So they receive good quality energy, and they exchange with the environment energy of low quality, and that's a way of keeping their inner entropy low, but with a high price of always increasing the entropy of the universe. And also in complex systems, we have a strong emergence. So there are new properties that make no sense at the lower level. So in this case, these hexagonal structures, again, have no meaning from the point of view of atoms and molecules of water, of oil, or whatever this liquid is. The idea that's behind this complexity, this emergence of complexity in nature, is the emergence of attractors in phase space. So this is a very simple picture of attractors. Imagine that each one of these diagrams is a phase space of whatever system. But you see that there are some regions of the phase space where the probability for the system to be is higher. So attractors are zones, are places in the phase space in the microscope in the microscopic possibilities that are more likely. So you could think these diagrams could represent the weather forecast, the weather evolution. So depending on the initial condition, you could end up having a rainy day or a sunny day, or you could end up having maybe a stormy day, so some gale or whatever. Or maybe this last case would be the case of my home city. This is the case where it doesn't matter where you start, you end up always in this situation. It means rain, always raining in my home city. But so again, the idea is that we have in nature this emergence of attractors, this concentration of dynamics in some regions of the phase space. And this can be applied to the tree of life. So this is a beautiful picture of how life started, perhaps from this Luca, this last universal common ancestor. And you see all these differentiation and variation and all a huge number of species. But during all this evolution, what we have is a restriction of the phase space. So we have attractors and attractors and attractors that are constraining the possibilities of evolution. And at the same time, they are providing new possibilities for evolution. And it seems really cavalier, it seems really arrogant to think that we can predict how evolution will go because we don't even know what the relevant degrees of freedom are of evolution. So the key idea of all this discussion of complexity is that this emergence of attractors is really not predictable in a bottom-up fashion. So we always need to have more information from the upper levels in order to make head or tails of our theories. Otherwise, we cannot describe this situation scientifically. Of course, one could still say, well, just think about typical interactions between the genes of a bacterium. One could still stick to the view of, okay, it's only the initial conditions and a very exceptional dynamics of the universe that allows this specific form of evolution of the emergence of life on planet Earth. The point is that can we decide, can we discriminate between weak and strong emergence? So is this only weak emergence? So it's only a matter of, well, the huge amount of degrees of freedom, but it's only because of the limitation of human knowledge that we cannot predict evolution. But in the end, everything is determined and everything follows some specific microscopic rules. Or is it the case that we live in a universe where strong emergence happens? So there's the true creativity and emergence of new properties of new systems that cannot be predicted from scratch, because we don't even know what the new degrees of freedom are going to be. Now, if we move to the third part of my talk, so I think that we have strong reasons to believe that emergence is strong. It's not just a matter of limitation of our knowledge. So maybe some of you are familiar with the problem of quantum mechanics, and I'd like to dub this part of my talk of the intrinsic duality of quantum mechanics. And I think this is also a singularity. This is singular because this is our most fundamental theory. Of course, we have relativity theory, but it seems that relativity theory is going to be quantized somehow, maybe with superstring theory or with another theory, but quantum mechanics has arrived, and we don't think that we can have a classical description of the universe anymore, so a deterministic description of the universe anymore. So why quantum mechanics is relevant for our topic today? Well, I'm very likely that you've heard about the measurement problem in quantum mechanics. So why we have this measurement problem? Well, in quantum mechanics, we have two very different procedures to describe the dynamics of any system. In the one hand, we have a unitary evolution that is described by this Schrödinger equation. It's a deterministic equation. In that sense, this is very classical. So the basic object here is the wave function psi, and it follows a deterministic equation. And once we have the boundary conditions and we have the initial conditions, we can solve and we can find the solution. The point is that since this equation is linear, any combination of solutions is also a solution. So we may have many different solutions and different sums of these solutions. The point is that when I perform a measurement, I only obtain one result. So among all these possible wave functions, I only obtain one of them. Well, more technically, I would obtain only one result of the observable. So the wave function is said to be reduced. The wave function is collapsed or reduced. And this is a highly nonlinear procedure. So we call these two procedures like unitary evolution, U, and reductive evolution or reduced evolution, R. So it seems that nature behaves like this strange dance of unitary evolution and reduction of the wave function. Unitary evolution and reduction of the wave function. And this is weird. This is really weird because why a measurement, why the performer of a measurement should be something different from any other physical process that is described with this unitary evolution. So this reduction of the wave function only happens when I perform a measurement, when I gain information about the result of my measurement. So why these two different procedures? Well, this is the measurement problem. So what measurement has as special in nature? Now, there's a huge amount of discussion about this, and this is related to the interpretation of quantum mechanics. But the point is that this transition from the unitary evolution to the classical world is unclear. So it's blurred. We have an ill-defined border. So we have this border where in this part we have quantum mechanics and superposition of this Schrödinger cat. I will say something in a moment. And we have this part where the world behaves classically. We have well-defined magnitudes, and we can say that the particles are in a position or a different position, or have this velocity or a different velocity, or this momentum or different momentum. But actually, we don't know. We don't have a clear-cut argument or clear-cut magnitude, quantity, to discriminate between classical and quantum domains. And the situation is different from relativity. So if you are interested, we could discuss why it is different from relativity, where we have this very good clear-cut limit depending on the comparison with the speed of light. Now, quintessentially, I would say that this problem of transition from the quantum to the classical world is epitomized with the Schrödinger cat. So imagine that I have a cat in a box, in a closed box, and then I have maybe a radioactive material. And since this radioactive material can decay or not in a certain amount of time, in principle, it is in a superposition of decaying and not decaying material. So if it decays, then it triggers this mechanism, and then the hammer falls down and breaks this vial with poison, and the poison is released, and the cat is poisoned, and the cat is dead after some time. But of course, if the radioactive material does not decay, then all this doesn't happen, and the cat is happily alive. So in quantum mechanics, in as much as I'm not doing a measurement, I'm not performing a measurement, the cat would also be in a superposition of being dead and being alive, until the very moment in which I open the box and I see what the result is, whether the cat is dead or is alive. Now, this is really weird, because is it really my opening the box that makes the cat dead or alive? So this is the problem of transition from the quantum to the classical world. So now let me be a bit more specific about how physics and quantum physics has tried to come to terms with this problem. And maybe you have heard about the Coherence Program. So how the coherence, that is something that also happens in nature, could solve this problem of the transition from the quantum to the classical world. So the idea is that in real life, systems are continually interacting with the environment that has many, many particles. And with this interaction, some of the weird properties of quantum mechanics fade away. So for instance, this when we have waves, we have sorry, I missed the word. We have interferences. When we have waves, we have interferences. Now, when we have many particles, the specific relation between phases are lost unless this interference pattern disappears. So this is, imagine that this is a 2 by 2 matrix, and each element of this matrix represent, would be dead and alive cat, alive and dead cat, alive and alive, dead and dead. Then with decoherence, if decoherence is working, in the end, after some amount of time, these strange possibilities of a mixture of dead and alive cat go down, and we keep only the classical probabilities of a dead and dead cat and alive cat. So the probability amplitudes become classical probabilities, and everybody is happy with that. So this is our presentation. So this superposed state doesn't work anymore. It's no longer physical because thanks to this interaction with the environment, it evolves to a classical mixture of being alive or being dead. Now, what's the problem with this? So does it solve this measurement problem, the decoherence in quantum mechanics? Well, let me be more specific. So let's imagine that we are dealing with a measurement in quantum mechanics. So imagine that I have a system in a state Si represented by this ket vector Si, and then I have a measurement device that has some pointer state that should tell me what the system state is. Now, when they interact, if the device is good enough, then this device will show that the system is in state Si. So the pointer shows the mark, this result I. Okay, now this mathematically can be shown to be this evolution. So initially, since we can have any superposition of states in the system, so we could have many Si, and all of them can be possible state of the system, I would have this tensor state, and it evolves to this superposition of Si's and state of apparatus. The device would be in the state AI. So this is always like that. The formalism shows that I can always find, so if the apparatus is reliable, if it is working well, I do not obtain interferences between I and J states. I always have I and I states. Now, please notice that this is absolutely something formal. I'm not saying what these states represent. For the time being, I'm not saying anything about what these states are representing. Now, let's introduce the observer. And so what would happen with the observer? Well, I still have my system and the measurement device interacting. So it shows the state I, if it is reliable. And then, of course, the observer should be in a state, in physical state OI. So the observer in the state I, that corresponds to seeing the apparatus in state I, that shows that the system is in state Si. So again, mathematically, with the observation, I would have this tensor product of I states, system in state Si, the device in state AI, and the observer in state OI. Now, again, this is only the formalism. I'm not saying nothing about the real content of these states. So physically, what these states are representing. Now, the question that I want to stress here is the problem of the emergence of the preferred basis. So what actually are these physical states? Now, let me show you what the solution given by Wojtek Surek is. Wojtek Surek is a well-known physicist, one of the founding fathers of this decoherence program, and he tries to provide a solution to this question of decoherence and how these observer states correlate with our perception of states, of what is called qualia, the way how we experience the world. So this is the solution provided by Surek. He says this: one might still ask why the preferred basis of neurons, so our neurons, our cerebral states, becomes correlated with the classical observables in the familiar universe. So one thing is the neuronal correlates, and another thing is what we observe. And he says this: our senses did not evolve for the purpose of verifying quantum mechanics. Rather, they have developed in the process in which survival of the fittest played a central role. So there is no evolutionary reason for perception when nothing can be gained from prediction. And as the predictability sieve illustrates, only quantum states that are robust in spite of decoherence and effectively classical have predictable consequences. Indeed, classical reality can be regarded as nearly synonymous with predictability. So in other words, what Surek is trying to convey is that all these states are stable, so they become classical states because they are predictable. Now, what's the problem with this interpretation? By the way, it's called the existential interpretation. So the problem, the flaw with this interpretation, with this allegedly solution to the problem, is that there is an epistemic confusion. So one thing, as I try to tell you, so these are the neuronal correlates of our vision. So our vision of a system in a specific state Si. So these are the neural correlates, visual system. And another thing is that we observe the system. So we perceive the system in this state Si. So in other words, one thing is the neuronal correlates, for instance, of an apple being red, and another thing is that I see red. So red is not a physical state. So physical state would be entangled with my neuronal correlates, etc. But these are two different things. In quantum mechanical formalism, there is no place for these qualia states. If you wish, the problem behind this interpretation is that the neuronal correlates or neural correlates of the observer, of the perception of the observer, is different from the fact that the observer perceives Si. For instance, when Si is red, the color of my system. So perceiving red is different from the neuronal correlates perceiving red. And so the problem with this interpretation is that predictability plays no role in the whole formalism of quantum mechanics. And that's why we need to introduce classical observations to make head or tails of the formalism. Otherwise, from the sheer formalism, we cannot obtain this correspondence with reality. That's why in quantum mechanics, from the very beginning, we need to introduce the correspondence principle to say how our formalism establishes this correspondence with observations. And this is something that the founding fathers of quantum mechanics had very clear from the very beginning. I love this quote by this young Werner Heisenberg, who explains that classical physics is inevitable even for quantum physics. So he says this, that the concepts of classical physics are an essential part of the language which forms the basis of all natural science. Our actual situation in science is such that we do use the classical concept for the description of the experience, and it was the problem of quantum theory to find theoretical interpretation of the experiments on this basis. Please recall that quantum mechanics appears because we need to understand, we need to explain what the levels of energy of the hydrogen atom are, why those specific energy levels for the electron in the hydrogen atom. So what Heisenberg is trying to say, and it seems that this is something unassailable in the interpretation of quantum mechanics, is that we need to make our theories counting on our observations. So our scientific work in physics consists in asking questions about nature in the language that we possess. In other words, according with our observations, it seems impossible that we make sense of quantum mechanics without this observation, without introducing this further physical information about what we measure, to make sense of the meaning of the symbols. Now, this is, in a sense, for classical physics, this is trivial, because when we write down a symbol like velocity, we think that this symbol corresponds very easily with the physical velocity. But this is the real problem in quantum mechanics, and it has to do with the interpretation of the wave function, the ontology of the wave function. We have symbols that have no direct correspondence with something that we observe. So we need to introduce these additional cognitive assumptions to make sense of the theory. And that's why the coherent doesn't work to explain the emergence from the quantum domain to the classical domain. So I'm approaching I think that 1 hour talk, and I think I have still 10 minutes. And let me talk very, very briefly about the Four Singularity, as I like to see it in nature, and it has to do with the question of information and the symbol grounding problem. It's related to the problem of naturalization of information. Now, information is now a fashion concept in science, and well, there are reasons for that, but at the same time, it's a very controversial concept because, as many scientists say, so information seems to introduce some subjective background because it's information for whom. It's unclear that information is present objectively in nature without any consciousness or without any agent for whom this information is relevant. Now, I think I like this book by Luciano Floridi. He's a professor in Oxford University, where he explains the very basis of information, and he distinguishes different types of information: semantic information that needs information that is relevant and is well formed, is syntactically formed, and is meaningful. He also distinguishes knowledge as semantic information that is properly accounted for. And well, he shows how we humans are very special in the universe because we can grow information in reality. We can grow knowledge in reality because we know to distinguish information that is relevant from information that is not relevant. And not only that, but we discover new information that is relevant. Just think about gravitational waves. So maybe in the Middle Ages, gravitational waves were not an issue, but now they are, because we are able to discover new information, new meaningful information, and we account for that information. So we are building this edifice of science, beautiful edifice of knowledge. And okay, and reality would be the totality of information. Now, my point here is that when Luciano Floridi tries to deal with this symbol grounding problem, so that how symbols emerge in nature, we are in a species that deal with symbols. We have symbolic language, so we know what a symbol is. But is it possible that a symbol appears without a reference to a consciousness or some agent or some human being? Now he tries to answer this problem with a nice explanation. Well, he tries to explain how symbols could emerge in a naturalistic way, or if you wish, in some artificial intelligent device. I'll try not to go into the details, but the idea is that if I had a machine that interacts with the environment at some level of abstraction, LOA1, imagine that I have some robot and it hits a wall, and then it knows that every time it hits a wall, it must turn right. Then hitting a wall makes that the machine is in state 1. That means turning right. Okay, so the output turning right every time that it hits a wall. So the function of the environment hitting a wall means turning right. Okay, so the idea of Luciano Flori is perhaps I could have some other part of my machine, a machine 2, where I have some set of symbols, and then I associate one symbol of this set of symbols to every state of my system. So state S1 is associated with this symbol 1. Of course, this should happen at a different level of abstraction, because I have here two different procedures. So one thing is the state of the system in hitting the wall, and another thing is assigning a symbol to this specific state of the system. Now, combining these two things, I could have maybe 2 levels of abstraction, and the machine would develop this association of symbols with each one of its internal states. Of course, the problem with all this construction, it is that somehow it violates what is known as the zero semantic commitment. So there is no way to introduce these symbols if we don't have some translation, if we don't have some programmer who tells the machine how this correspondence must be done. Because otherwise there is no need for the machine to devote some symbols, some abstract symbols to these internal states. If you wish, in other words, there is no way, there is no rationale for the machine to develop a language, this symbolic language. It has to be introduced by the programmer in some way or other. So there is always a translation. If you think about artificial intelligence, there's always a translation of information, of external information, of environmental information into numbers. And that means a translation, and that means some representation that depends on the programmer. So this remains a problem. How does the symbol, how do symbols emerge in nature? So how does symbolic language emerge in nature? I think it has to do with what we know as immaterial knowledge. And well, this is a very specific feature of human beings. If we think of evolutionary framework, and we think of this evolutionary framework as a mixture of persistence and adaptability, so I need to devote resources for keeping my identity, but also I need to devote resources for some change, because otherwise I cannot catch up with the environment. Then the greatest possible plasticity in nature is that provided by immaterial knowledge. This is, I say, a specific feature of the human being, because human beings are capable of constantly redefining the context. So it is as we don't feel comfortable. We don't feel done with a single context, and we are always looking for new possibilities, new ways of dealing, of negotiating the environment. And well, that has to do with this immateriality of human knowledge and this creativity of human beings when interacting with nature. So of making new theories, of posing new problems, of trying to figure out how the universe as a whole works. Well, this is an explanation on how this immateriality of knowledge could appear in this evolutionary framework. It would be a sort of phase transition where this informational flux closes in on itself. And this would be the fourth singularity. And since we are running out of time, I will skip the details. But the idea is that it seems that the human soul is what allows this immaterial possession of information that classical philosophy dubs like knowledge. This knowledge is intellectual knowledge, immaterial knowledge, this immaterial possession of forms. And that's why we don't need to risk our life every time we interact with the environment. So we are out of this cycle of trial and error. So we are able to interact with the environment through culture, through the exchange of ideas, of these immaterial ideas with other people. Well, I will skip this, and I would like to end my talk with what I call the Big Singularity. These are two beautiful pictures. So it seems that we live in a world, in nature, this ontology, this ontological realm, where we have the emergence of some epistemic organism like us that develop this immaterial knowledge. And in this realm of epistemology, of immaterial knowledge, well, there are some islands of ontological consequences because our knowledge changes the world, has consequences for the world. Or if you wish, maybe some of you are familiar with this picture. This is Penrose's three worlds in the road to reality, where we have a physical world, and part of it influences or is a necessary cause for the mental world. And of course, since Penrose is a Platonic, he thinks that part of the mental world connects with the Platonic world of mathematics, and part of mathematics is able to describe all the physical world. So there's this relationship between these three worlds, and this relationship is not convergence. There's not a whole picture that can explain these three relationships, because it's only a part of this that influences this, and only a part of this that influences this, and only a part of this that influences this. So we don't have the whole picture of this psychophysical interaction. And so we are approaching what I would like to call the Big Singularity. This is a beautiful quote by Albert Einstein talking about what he considered like the big miracle in nature. What's the big miracle in nature? This is a letter to Maurice Solovin, a friend of his. It's a Romanian philosopher. And he said this. He spoke about the comprehensibility of the world as a miracle or as an eternal mystery. And he explains that one should expect the world to be subjected to law only to the extent that we order it through our intelligence. And this would be like the alphabetical ordering of the words of a language. Well, you know what a dictionary is, and you know perfectly well that you may have a dictionary, but you don't know the language, even though you have the dictionary. You may have a Polish-Spanish dictionary, as in my case, but I don't know Polish, even though I can look for the Polish words and try to translate them into Spanish because I have this correspondence. But this is not knowing the language. A language is something deeper than a dictionary conveys. So Albert Einstein explains that in a Newton theory of gravitation, for instance, the thing is wholly different. The success of such a theory, of such a project, presupposes a high degree of ordering of the objective world. And this could not be expected a priori. That is the miracle. So the intelligibility of nature, that is called a miracle by Einstein. And very cleverly, he says that there lies the weakness of positivists and professional atheists who are elated because they feel that they have not only successfully read the words of gods, but bear the miracles. But he stops there. He says, we must be satisfied to acknowledge the miracle without there being any legitimate way for us to approach it. So he acknowledged the miracle. So this correspondence between nature and our mind and our knowledge of this intelligibility of nature, that we can comprehend nature, we can understand nature step by step, little by little, but we comprehend nature. But he remains there, just acknowledging the miracle. But now compare this quote with this other quote by Pope Benedict XVI. In 2006, he said this, speaking about mathematics. He says that mathematics is a creation of our intelligence, but the correspondence between its structures and the real structure of the universe arouses our admiration and raises a big question. It implies, in fact, that the universe itself is structured in an intelligent manner, such that a profound correspondence exists between our subjective reason and the objective reason in nature. So he goes beyond Einstein. So he takes believers and leads them beyond this just acknowledging. The Pope Benedict XVI says that it then becomes inevitable to ask oneself if there might not be a single original intelligence that is common font of them both. Thus, so this way, precisely the reflection on the development of science brings us towards the creator logos. So precisely reflecting about this big singularity, so the intelligibility of nature, we could reach this creator logos. And I would call this all this talk about singularities, this exceptionality of the universe from the viewpoint of physics, where things are really weird in some aspects. These singularities with small letter, I think that, at least for us believers, lead us to the big singularity, God himself. At least this is the message that I would like to convey you. And so I will stop here. I thank you for your attention, and I think we have some time for questions. So thanks for your presence and your support.
Very good. Thank you very much for your inspiring.
Yeah, let me see if I can
through the universe.
Yeah.
Thank you. Thank you for that very nice talk. I'm a physicist. I'm in Canada, in fact. And I mean, the question arose in my mind early on when you mentioned the God of the gaps, because as a physicist, I try to convey to people who are interested that how physics somehow drives me towards the idea that there is a God, and that's what I think that's what you concluded with. That's the conclusion of all these examples you gave. But I guess the question then arises: how do you defend that from people who will say, "Oh, you're just creating a God of the gaps because you're finding all this mystery in some of these the four singularities you talked about, and there's some belief amongst scientists, at least, that these will be resolved in due time by scientific methods, and they don't indicate anything."
Right. Yeah, very good questions, and I thank you for that. Well, I would say the following. I think there are gaps and gaps. Not all gaps are the same gaps. Of course, that's obvious. But the idea behind these singularities is that they seem to be very fundamental, and somehow science need to assume them, or to presuppose them, or in other ways need to go with them in order to follow its usual procedure. Let me be more specific. So just imagine a theory of everything. So we would avoid the God of the gaps if we had a theory of everything. But how would a theory of everything look like? Well, for sure, you would still need some parameters. You would still need some initial or boundary conditions. Perhaps you would need some symmetry breakings. As a physicist, you know that physicists like to think to try to get to this unification. through symmetries, this idea, powerful idea of symmetry, and beautiful idea. So the point is that nature is, at the very end, is underdetermined from our theories. And in that sense, it seems as if science itself needs some presuppositions, needs some assumptions that cannot explain, but it has to assume. And my view is that these singularities, so the past hypothesis, or the measurement problem, or the very fact of the presence of a complex dynamical system, has to be assumed. It's like a sort of phase transitions that cannot be predicted because we don't even know what the degrees of freedom are. So there are new degrees of freedom appearing in nature. That's the way I would try to convey the relevance of these gaps that are not just epistemic gaps. So they seem to be, they point towards some ontological gaps.
Good. Thank you.
All right, thank you. Are there any other questions?
So Gavas
has raised his hand. Gregos?
Hi, Javier. It's
Hi.
Wonderful
Good to see you. Yeah.
Well, so many subjects that it's really difficult to concentrate on one of them. I missed your lecture some years ago in Toruń about rising complexity, and you just mentioned with single word, Prigodin, and rising complexity. Do you think that our universe has this hidden feature of ability to rise the complexity, which would be against the second law of thermodynamics?
Yeah, thank you, Professor, for your question. So the short answer is yes. And so I would agree here with theoretician, theoretical biologists like Stuart Kauffman, who speaks about some new law of complexities, this increasing complexity of the universe. But the reason is that, what's the alternative to not having an increasing complexity? I think that the only alternative would be what Rovelli presents in his book, The Order of Time. So basically he says that, so we believe that we are thermodynamically special, and the Big Bang had a tiny entropy, actually because we are interacting only with a very, very small amount of degrees of freedom. So he claims that the universe is really much bigger, and it has many more degrees of freedom, and all these degrees of freedom are truly in equilibrium. So actually the universe is a big cycle. So it's repetitive, it's a big cycle. The only thing is, because of our particular configuration, and we are interacting only with a small amount of degrees of freedom, that, well, turn out to be in a fluctuation. So in other words, we are a fluctuation in a much bigger universe that is in thermal equilibrium. So I think that's not fair. I think that in science, we need to stick to what we see and the degrees of freedom that we experience. And I think that that solution raises more problems than it solves, because it's like saying, okay, there are many more things, and it's like the multiverse, if you wish. So but that begs the question. So okay, so first of all, what's the evidence for that? And second, well, still, why do I have this configuration that is so special that I seem to be in a fluctuation in a much bigger universe that is in thermal equilibrium? It's a sort of nonsense. I think it's not fair. That's my view. So I think it's really fundamental to live in a universe with a strong arrow of time, and that it starts in a very non-equilibrium situation. It's very far from equilibrium. Yeah.
Rovelli is my friend from Trento, but I totally disagree with him. I agree.
Okay. Me too.
Thank you.
Okay, are there any other questions? Maybe while waiting for it, let me just comment on this. I wouldn't be so critical about the multiverse approach. We've reached a stage in physics where we discuss, we raise questions for which we have no ways of answering, of exploring them experimentally, not even in principle.
Yeah.
Right? So this is a sad reality of today's physics, at least cosmology, fundamental physics. And therefore, invoking an issue of multiverse, which by definition cannot be observed, in itself, of course, raises discomfort. But at the same time, if we theoretical physicists make a construct, a theoretical construct, which ultimately is self-consistent and gives an explanation of puzzles of our universe, then we can say that there is at least a chance that this provides a correct solution. Of course, we cannot verify it experimentally, but at least it's not a completely idiotic game to do it. It's not completely senseless. We can create a theoretical construct which can provide a possible solution. So in this respect, I would be defending the multiverse approach wherever is necessary, when there are no other ways exist. On the other hand, making unwarranted assumptions about the multiverse, that's another matter. And then I would agree that there might be something that raises more questions than answers.
Yeah, thank you. I think it is Max Tegmark who says that everything that follows logically from a well-established mathematical equation should be accepted as also existing. That's more or less the idea of the argument. But I think that's quite controversial. I'm not so sure about it because, well, that makes existence is equivalent to possibility. And I think so our knowledge continually deals with factual realities, actualities, and also counterfactuals. So things that logically are possible, but however, we consider them not to exist. So I think that's, at least it's problematic, that sort of argumentation. On the other hand, I agree. I think that it's really valuable to develop a theory of multiverse. As far as I know, the multiverse, well, stems from inflationary theories, and also in the framework of superstring theories, we have many possibilities of constructing the compact dimensions, the compact space that in which these 6 curled dimensions are wrapped up. So it seems that you have like a 10 to the 500 parameters to construct your universe within the multiverse. Now, so, okay, I have no special problem with that. I think that's mathematical physics. Of course, we need to be down to earth. We need to come to terms with experiment at some moment. So it has some value, but not has an absolute value. And I would expect for some discrimination, for some tests. But I think that still multiverses have this problem of typicality. So even in multiverse, our universe, so the universe that we know and that is hospitable to life, it's extremely rare. It's not typical. And I think that you need a better explanation. So you cannot simply say, okay, the multiverse is that, and one of them, by chance, by sheer chance, develops the parameters that you need for life. But I don't think that's a fair scientific explanation. So you would still have to say something else. at least that's my view, and that's my contention. That's my problem with multiverse. So you need to say something else.
Well, certainly, it's not a comfortable approach to invoke an enormous amount of number or zillions of other universes in order to explain the features of our universe. But in itself, it's not completely unscientific, as I said. By the way, I didn't say what Max said, that whatever is mathematically possible is real. So I don't subscribe to this view. But what I'm saying is that it was in fact indeed in the search of, in the superstring approach, in the search of a unique vacuum that would correspond to our vacuum, to our universe. Mm-hmm. It was realized that there are in fact zillions of possible vacua, each leading to a possible universe, not necessarily realized in nature, in this multiverse nature. But in this approach, we just say, or it is just said that our universe corresponds to a vacuum, a possible vacuum, which is indeed exceptional. It's exceptional in the sense that it can host life and therefore observers who can ask questions. Why do we live in such an exceptional universe? It's not scientific in the traditional classical sense. It's uncomfortable. I've had biggest discomfort with this approach myself for years, but I concede that this might be sort of the only or one of the very few fruitful approaches which can lead us to something at least. But well, that's my view. Some people take it.
No, I thank you for the remark. If I may say something, so I think of course that it's absolutely you have the right to develop a multiverse theories, and it's really valuable in that sense. What I'm saying is that our universe is exceptional because in all the measures that you have to distinguish, you need to introduce a measure to distinguish between universes in the multiverse. So a measure saying, so how close universes are, or how fundamental parameter or vacua are different between themselves. So my point is that our universe is still exceptional in the sense that life is very, very, biofriendly universe is extremely rare. And even if you go to quantum mechanics, so you have the problem of factorization of quantum mechanics. So it's very, so something like locality that we experience every day, everywhere, is something very, very strange if you start from a very generic Hilbert space. So these sort of things is what really worries me, and that demands some scientific explanation. And so you need to go beyond that. So I'm open to go beyond that, but definitely you need more than saying, okay, so one of the possibilities is realized because there is some symmetry breaking. And I think that we sweep underneath the rug some of the problems of physics when we say, when we invoke some sort of symmetry breaking. So what's the ontological state of symmetry breaking? What's that?
That's a good question, I guess. Okay, I can see Grzegorz raising his hand again. Is this correct?
No, I'm not raising my hand. I'm saying that this is just sweeping things on the rack, saying, using some expressions which are ready, let's say, and we don't go into very meaning. Wonderful. Thank you again, Javier.
Okay, so are there any other questions or comments? I cannot see any at the moment. Maybe one thing that I wanted to clarify. You've used the concept of singularity in your talk several times. Now, I'm a particle physicist, To me, well, not only to me, but singularity seems to be associated with infinity. You know, something that we believe in real universe simply doesn't exist. It's if we encounter an infinity in our calculations of physical quantities, we know that we've hit something. We've done something maybe not necessarily wrong, but we've hit the boundary. We need to go to another description in which the singularity would disappear. So what is the meaning of singularity?
Yeah,
you used in your talk?
You are right. I'm using the term singularity in a broad sense. So I'm not strictly speaking about infinities, even though, well, yeah, perhaps you should go into the details. For instance, first singularity, the extremely tiny entropy at the Big Bang. So it's not an infinite, but this huge number seems to point towards something really deep that we are not taking into account in our explanation. So we need some sort of different explanation because it's really huge. So it seems that you don't have any good explanation within current physics to make head or tail of that number. So when I was speaking about singularities, implicitly I was thinking about some phase transition. And I like the concept of phase transition because in a phase transition, so you have a different regime and probably you have new degrees of freedom, so a new description. And how do we cope with phase transitions? I think we have these renormalization group techniques. And my point is that perhaps renormalization group works in some theories, but my intuition is that in these four singularities, renormalization groups doesn't work. So you need to go beyond. Well, if you wish, I'm just saying that so physics cannot explain the whole universe from scratch. So you need to introduce more information from higher levels. And in my view, that's a clue pointing towards true novelty, creativity of nature itself, this ontological emergence. So it's not just epistemic emergence. So a new description because we've been too bad with our previous description. So you need a new description inspired by what nature really does. It's something new. And that's why I think that...
Are you saying this as a physicist or a priest? As a physicist, are you saying as a physicist that you need something to describe the universe, something beyond physics? Do I understand it correctly?
I would say, as a scientist, as a physicist, I would say that you need something beyond physics to describe the universe. But I would like to clarify this by saying that it's information at different levels. And just to make sure that my view is understood, what I'm claiming is that when you try to translate between different levels, this translation, these laws of translation, just think about from atoms to molecules, from molecules to proteins, from proteins to cells, from cells to tissues. So you have this translation, these coarse grainings. My impression is that these transitional laws for coarse graining are not convergent. So they are like, so they have some sort of being ad hoc. So there is no whole rule for coarse graining in the universe. In other words, physics always work within a regime. So I'm really pessimistic about the possibility of a theory of the universe, about a possibility of a theory of everything.
Thank you.
But of course, I may be wrong as a scientist.
We may all be wrong. All right, I'm good. So we know these are very, very deep fundamental issues that we're talking about here, right? At the boundary of what is being discussed. Okay, I think we have a question from Krakow.
Thank you, Leszek. There is a question from myself, actually, because from the audience so far, nothing, but maybe we'll have questions later. I just wanted to express my personal doubt about the main point of the lecture, which was, by the way, very interesting, very inspiring. I'm a physicist, and I have a difficulty with calling our universe exceptional unless we experience other universes. We do not have any experimental knowledge, any insight into the other possibilities. So how can we be sure that our world is not the only possible installation, so to say? So this is also going towards criticizing the anthropic principle as a theistic argument. So can you comment on this?
I absolutely agree with you in criticizing the anthropic principle. I think there's a beautiful argument by Penrose explaining why the anthropic principle doesn't work. The anthropic principle doesn't work because so the evolution of the universe as a whole is much more expensive, statistically speaking, than the creation of human beings from the clash of atoms in the solar system. So in other words, the universe is much beyond thermodynamic equilibrium than needed for creating intelligent or sentient beings. So in that sense, I think the anthropic principle doesn't solve the issue either. And I'm calling the universe exceptional, not by comparing it with extant universes that we don't know, but simply by saying, well, with our theories, I need to introduce additional assumptions to get them isomorphic with actual physical processes. And this information that I need to introduce is really exceptional in the sense that it seems to be like a set of measure zero among the possibilities, among just the mathematical or logical possibilities. Of course, one needs to be careful when saying that, because so you should go into the details of in what sense, how could we measure the entropy at the Big Bang? Is that a good calculation? What Penrose has shown, this number? Well, there is some controversy, but it seems that the past hypothesis is inevitable. Or, for instance, the configuration, the constitution of complex systems. So in philosophy of nature, there is a controversy regarding this constitution because it seems that you need to introduce some sort of circular causality. In other words, only with this bottom-up approach, you don't explain the emergence of complex systems that exert some sort of top-down influence into the lower levels. So we tend to so how do we deal in physics with this? Well, we introduce boundary conditions, we introduce initial conditions. So we introduce information at a different level that allows us to use our equations. But in a sense, I think that's cheating. Well, of course, that's not cheating, but I think that one must assume, one must acknowledge that you are introducing something that it's not a whole explanation. So it's an explanation valid for a specific regime, but you are not explaining the emergence of the whole complex system, or you are not explaining, for instance, the emergence of the classical world from the quantum world. Nobody knows how that happens. And my view is that perhaps there's a determination of nature itself that goes beyond what physics can describe. So we must assume that nature determines itself in ways that go beyond our physical descriptions. In a sort, like what happens with human freedom, with human free will. So I don't think that you can describe a human being only physically, because we have this free will. And just to finish my argument, I remember some words by Joseph Ratzinger explaining that this sort of universe, this behavior of nature with different degrees of self-determination, is perhaps what one would expect from a personal God. So a God that really gives some proto-freedom or true freedom to his creatures.
Oh, well, this discussion is becoming really interesting. Maybe I can just quickly respond to Piotr's issue with the word exceptional. It's indeed, using the word exceptional is a bit misleading, right? Because it suggests that there are many universes in which our is exceptional. It's not the way it is meant in, at least in the physics, in the domain of physics that I work on. Our universe maybe is not exceptional, but it's special in the sense that some key parameters that describe the universe have values which are hard to understand. The density, the mass energy density of the universe is extremely close to the critical density. In fact, not only now, but at the beginning of the universe, at the Planck time, it had to be very close to unity in less than 1/10 to the power 60. And the question arises why we have some parameters like this in our universe. This is a very special universe that we live in. And interpretations or explanations come from various directions. Entropic principle, a weak entropic principle at least, is not as idiotic, I would say. It's not that as unacceptable, because the fact is that in our universe there are observers. We don't know about other universes. But there are other approaches. So it's an ongoing discussion.
Yeah, I would be happy also with this, with a different title, the special universe. So I think that exceptional was a way of, maybe making things more interesting. But so I'm also happy with this description.
So yes, epistemology, language is very important in whatever we try to explain, as you pointed out in your lecture. So may I ask? So thank you again for your inspiring talk. Certainly left us with lots of issues to think about. And I hope it's not the last time that you are joining us. And I think because of your constraints, we need to finish now. Can I ask Father Piotr to give the final blessing?
Jest prośba o
Could be
błogosławienie.
Latin.
Okay. Pan z wami.
Z duchem Twoim.
Niech was błogosławi Bóg Wszechmogący, Ojciec i Syn i Duch Święty. Amen.
Amen.
Warm greetings from Toruń also. From people here.
So thanks a lot for your presence. And well, let's hope that we can work together, because I think this Society of Catholic Scientists is really promising. And my intuition that between Spain and Poland, we will have a lot of relationships with this. Okay.
We hope so. We hope so. We hope that this is the initial meeting of the many meetings in front of us, ahead of us.
Great.
Thank you.
So, bye-bye. Thanks a lot. Thank you ever so much.
Bye-bye. Thank you.
Bye.
Thank you.
Thank you. Bye-bye.
Carvas. Ciao.